I'm Dakota Brady, and this summer I am doing chemistry research with Dr. Shellhammer and Mr. Hudson. And our project is with the low energy laser spectroscopy, and it's a type of laser that Mr. Hudson has engineered to function a certain way, and it's similar to Raman spectroscopy. So here is our LELS instrument, and we have our laser in the bottom right-hand corner, the power source above it, the camera and the detector, which are very sensitive, and the grating. So peculiar properties about the LELS laser. We have no Raleigh scattering detected in our data, and we're firing at about 3 milliwatts. And this Raleigh scattering that is normally seen in Raman spectroscopy masks a lot of signals, but because we do not have the Raleigh scattering, there are no weak signals that are masked. And in regular Raman data, the Raleigh scattering is observed at about 180 to 200 milliwatts, and when we turn our laser up to about that energy, that is when we start to see our Raleigh scattering. We also do not have anti-Stokes lines. And what is a Raleigh line and what are Antistokes and Stokes lines? Raleigh scattering is an elastic scattering when the photon hits a molecule at a certain wavelength and then bounces back at that same wavelength. Stokes and anti-Stokes lines are the inelastic scattering of when the photon hits the molecule and then it scatters back at a different wavelength. This right here, this large peak on the right, would be the Raleigh line, and the small peaks would be the anti-Stokes and Stokes lines. And as you can see in our data, we are not seeing the Raleigh scattering and the Raleigh line. Another peculiar property would be that we do not have any fluorescence detected. Now, this means that we do not need gating. When fluorescence is detected, we lose a little bit of data in the spectrum collection, but because we don't detect that, we're collecting more data than the regular Raman spectroscopy collects. And fourth, we can actually obtain data of solids or liquids through opaque polypropylene bottles, which is unique to this laser because with a regular Raman laser, you need expensive attachments, but with our laser, we actually do not need these expensive attachments and are able to collect data of the solids through the bottles quite easily. So here's some of our LELS data for benzene. The black is the data that we have collected, and the red is the data that we have found in literature from Raman spectroscopy. And as you can see, our data matches quite well with the data that's found earlier in literature. And as you can see, I'd like to point out, we're collecting this data at 0.5 kilohertz. And here is what the spectrum looks like for the benzene at 0.5 kilohertz. We have 560 nanometers to 595 to 635 nanometers. And the spectra is clean and sharp. And here's a sampling of a few hydrocarbon liquids that we have collected. Again, I'll say that the red is from literature and the black is our data, and our data is matching and comparable with the literature's data. And I would also like to point out the low frequency that we are collecting at. And here are some floral compounds that we have also collected in the liquid state. And the green numbering would be where we believe the carbon-fluorine bond is located and where the peak is showing up. Also collected at about 0.5 kilohertz. Here's more sampling of our data that contain fluorine and more sampling. So next we're moving on to hydrocarbon solids. We began taking this data first from hydrocarbons, and this is iodoform. As you can see, the peaks are strong and defined and very clear, and this is at 15 kilohertz, which is still low frequency. We've also then moved on to fluorocompound solids, and this is pentafluorothiophenol. And as you can see, this is at 1 kilohertz, and we're still retrieving sharp, clear data. And I would also like to point out that with our laser, this is possible without the expensive extra attachments that regular Raman lasers do require. And here is a solid spectra versus the melt of that same compound. And as you can see, the melt looks a bit stronger and more clear than the solid. And this is the case sometimes, but it's also been the case where the solid looks more clear and defined than the melt. So it just is per what the compound is. And now what we're working on is taking collections of 5-fluorouracil. And here is a full spectra of what 5-fluorouracil is at 560 through 635 nanometers. And this is the structure of 5-fluorouracil. And 5-fluorouracil is right now being used in a lot of chemotherapy drugs. And we're using this, and we have the idea that we can be able to detect if fluorine can make its way into the tumor. Fluorine is not naturally occurring in the human body, so if we can use this laser to detect where the fluorine is and detect it in the tumor, that'll be success. And another form of this compound that's used is 5-fluorouridine, where a sugar is attached. And here's a sampling of our hydrocarbon solids that we've collected at relatively low frequencies. And here is a sampling of fluorine solids also at extremely low frequencies. And the green again is where we believe our carbon-fluorine bonds to be located. And in conclusion, we have unique qualities such as we're able to obtain the spectra of the solids through opaque polypropylene bottles without the necessity of having those extra expensive equipments and attachments. And we do not observe Raman lines and Antistokes lines and the Raleigh lines, which could mask the weak signals. And our energy is relatively low at 3 milliwatts as compared to a regular Raman laser at 180 to 200 milliwatts or higher. And our data is very comparable to the Raman data that has been found in literature previously. Thank you.